Thank you. Welcome back. My name is Tim Kelly, and my teammates are Luke, Wesley, and Ishmael. For our penultimate presentation of the day, we have a truly remarkable idea: artificial photosynthesis. As we all no doubt know, the fossil fuels that human society uses to meet the majority of its energy needs were originally formed through the process of photosynthesis. Our group is working with a project that's seeking to mimic this process, but in a more efficient and immediate way. We're working with a hub of scientists and laboratories formed and funded under the Department of Energy known as JCAP, the Joint Center of Artificial Photosynthesis. Our ultimate goal is to create high-density transportable liquid fuels. Given this ambitious goal, the project has considerable support and funding from the federal government. President Obama mentioned the process and project specifically in his most recent State of the Union address. And the project has received considerable funding, $122 million for its first 5 years of operation. What we want to emphasize at this point is that JCAP's in a very nascent stage. It was formed less than a year ago, but it has considerable ambitious goals for the next 5, 10, and 15 years to discover and develop cheap, robust, durable, and earth-abundant materials for all the pieces, to integrate them into a scalable system, and to be able to produce high-density, transportable liquid fuels. So the basic process emulates the natural process of photosynthesis, in which sunlight is absorbed, and that power is used to split water into its oxygen and hydrogen components. The hydrogen, which is then recombined with CO2 to make a usable fuel. Now, we have, within JCAP, they're focusing on integrating these steps. We have a value added from combining them. Our scientist has a patent-pending device that's able to integrate this so it can both absorb sunlight and split water. Now, the device used in order to generate chemically relevant voltages, it can use either a ferroelectric PV panel or some sort of, that's being developed by JCAP, or some sort of other commercially developed high band gap panel, excuse me. So the technology is at a very early stage. And because of this, we can't really calculate the exact cost or the volume of production that we can produce. But we still think this idea has tremendous worth. And to discuss a bit more about the actual value proposition of this idea, I'm going to hand it off to Wesley.
Thanks, Tim. So, looking at the ultimate goal for JCAP and artificial photosynthesis, which is to produce a cheap and reliable and sustainable liquid fuel for the future, our team came up with a few value propositions based on initial design parameters. So the first, as mentioned before, the biggest invention is to integrate all the process into one big process. So that would allow a higher efficiency and scalability of the device. Next, the design for the device is based on similar to a PV panel design. So the end product will look something like an artificial photosynthesis panel, and this design allows the device to be both distributed and modular. So it's going to be on-site generation where the fuel is needed, and modular is, so if the customer needs only some fuel, they need to invest in 1 or 2 panels, but if they need more, they just need to invest in more. So it's a linear relationship. And the next, the overall process is carbon neutral. There's no carbon emission. So this technology is green and very environmentally sustainable. And lastly, we expect that the feedstock price of sunlight and water won't be fluctuating as much as we see as the fossil fuel that's skyrocketing right now. So that's a good thing. And keeping that goal, in mind, it's like as mentioned before, the goal is pretty much far down the future, at least 15 years in the future. So what our team concluded that our best contribution to JCAP and the device is to come up with intermediate stepping stones. So what products from available products from this technology that JCAP can produce between now and that, reaching that goal. So 3 products that we came up with are the hydrogen and oxygen gas, and then methanol. The reason we chose the hydrogen and oxygen gas is because it's the obvious product from the electrolysis step, and also JCAP already has a prototype that can electrolyze water from just light. And we chose methanol as the first stepping stone into the hydrocarbon liquid fuel. It's because methanol is one of the simplest molecular hydrocarbon fuel to be synthesized. So the goal of our investigation is to characterize these current markets and come up with a target cost for the technology for it to be competitive in these existing markets. So the first deep dive we look into is the hydrogen market. And this market can be segmented into the different consumption ranges of the industry. So from the very small, we have the electronics, the chemistry research, and pharmaceutical industry. Then we have the food industry. Then the medium range, we have the metallurgy, metal process, and glass industry. And the largest consumer is the chemical industry, which includes oil refinery, coal refinery, and the fertilizer industries. And the total market for hydrogen in the United States is $22 billion in 2010. And that consumption range is 9 million metric tons of hydrogen in that 1 year. And it's interesting to see that 97% or almost all of the hydrogen consumed in the United States is only in these 2 large ranges of industries. So looking into the current technologies of generating hydrogen, we look into specifically electrolysis and steam method reforming, or SMR. So electrolysis only produces about 4% of the generation capacity in the United States currently, and it's mainly distributed, meaning it's on-site generation. And steam method reforming can be distributed or centralized, but it's high capacity production. It takes up 95% of the United States generation. And there are 3 main segments of hydrogen generation industry. We have in the blue, we have the on-purpose captive. In the red is on-purpose merchant, and in the green is byproduct. And based on cost analysis that we'll be going to later in detail, we decided that we can attack the on-purpose merchant segment the quickest. And to go into the cost analysis in detail, here's Luke.
Thank you, Wesley. So we looked on the cost side at both the production costs and the distribution costs. For production costs, we broke down the costs for the main technologies between feedstock, capital costs, and operations. What you can see is that most of the cost is actually related to feedstock, so natural gas for SMR, which is a pretty volatile feedstock, and also its variations are related to political events, so pretty unpredictable. For electrolysis, feedstock is obviously electricity, and the price of electricity in the US on the grid is around 10 cents a kilowatt hour, but that depends on how you generate electricity. So if you're distributed and off-grid with a PV, for instance, you're more at 15 cents a kilowatt hour, and it's also geographic dependent. In Hawaii, for instance, on the grid, you're above 20 cents a kilowatt hour. Now for the distribution. Obviously, distribution costs is highly dependent on the quantity you ship, and for small quantities, you would use cylinders, tube trailers, or cryogenic trucks. For larger quantities, you would use a pipeline. Obviously, the cost decreases with the quantity you ship. However, pipeline is only viable for very large quantities. The cost of shipping obviously also depends on the distance to which you ship your hydrogen. And that led us to look at the infrastructure in the US. Specifically, you see that the pipeline infrastructure is extremely limited and concentrated to Texas and Louisiana. And on this map, we have, so it's a bit hard to see, but we have basically all the hydrogen generation plants in the US and a radius of 100 kilometers around it. So there are obviously a lot of holes on the US territory. So we added both costs to come up with an idea of the target that the artificial photosynthesis technology should reach in order to begin to compete on these markets. And the first target would be distributed electrolysis. So for our target selection, we think that distributed H2 has a premium value of around $6 or $7 per kilogram of hydrogen, which makes it a great candidate. Moreover, the modularity of the system is pretty relevant for that kind of users. And last but not least, there are limited or almost no switching costs for these customers as compared to big SMR with installed capacity. However, there are a few operational factors to consider with the JCAP technology, and notably the fact that the output would be low pressure, which makes it hard to address markets where liquid hydrogen is used primarily. And also, because of the intermittent nature of solar, you would need to have storage to address markets where you have a continuous process, industrial process. So second, we also looked at oxygen, which is produced concurrently as the hydrogen in the process. We estimated the value of the hydrogen, the relative value of the hydrogen and the oxygen produced. So based on the premium hydrogen value we have determined before. And we see that oxygen would be only a byproduct with its current price. However, we looked rapidly at what the premium markets for oxygen would be. It's essentially medical gas, and there are many hurdles to overcome in that market, notably regulatory hurdles that don't make it really a likely target for us. So second, we looked at the markets where you could use both hydrogen and oxygen combined. There are very few of them, and those we identified have also huge hurdles for our technology. And now I'll hand it to Tim for methanol.
Thank you, Luc. So hydrogen and oxygen are important stepping stones. But ultimately, our goal is to get a transportable liquid fuel. And that's what we are looking at here, where the size of the respective spheres represent the relative size of the market for these different processes. JCAP is very clear that they don't want to be prejudiced or pre-guess which fuel they're ultimately going to mass produce from this process. They want to be experimenting and exploring different kinds to see what makes the most sense. In general, though, the more complex fuels are going to be more technologically difficult. But they're also going to represent higher markets because, in many ways, most primarily because they have a larger energy density per their volume. However, for the purposes of this presentation, in keeping with our stepping stone approach, we're focusing on methanol. Because it's the most chemically simple, we see it as the shortest technological path to get there. Now, methanol is currently used in many different products. There's a number of established markets, ranging from formaldehyde, which is used in pharmaceuticals and many other things, acetic acid, used in paints. Now, these are fairly well established. The demand is fairly happy with the supply, but we're also going to be looking at growth markets. These are areas where methanol is on rapidly increasing demand, both for fuel blending, where it's mixed with gasoline and used as an alternate fuel for vehicles, and in DME, when methanol is transformed to dimethyl ether, which is used as a propane substitute, very important for both cooking and heating. Now, this chart basically shows the demand for methanol in 2010 versus 2011 and how it's grown. For the past more than a decade, methanol market has grown at an annual rate of about 4.2%. But the past year and the projections for future years is that that growth rate will be over 7%. This is fueled in large part by China, which is rapidly expanding its use of methanol, particularly in the area of fuel. Chinese policy, a number of regulations passed in late 2009 that came into effect then, has regulated and demanded an increased use of methanol in the fuel used to power that nation's fleet of vehicles. So that's one of the major drivers of this. Now, in exploring the methanol market, we're basically repeating the procedure we did in hydrogen, looking at first the overall market, its future forecasts, and then getting into the production and distribution costs of competing methods of producing this product. So to get into those costs, here's Ishmael.
Thank you, Tim. So I will lead you through the economics of the methanol industry. First, we have here the process of one of the most widely used process of producing methanol, which is the steam methane reforming. So we have three main steps, three main processes. The biggest chunk of cost here would be the reforming phase, where actually you have you produce this mix of carbon monoxide, carbon dioxide, and hydrogen. It represents 60% of the overall cost, and the two remaining steps here are here to actually synthesize the methanol and bring it to a level of purity that is requested for further use. Then we've looked at the transportation and storage costs for methanol, which interestingly enough are a huge chunk of this cost. And why? Because there is mainly two figures that we need to keep in mind. The US imports 64% of the methanol consumed in US, and 70% of this importation arrives here in the hubs of Houston and Louisiana. Then methanol cost depends, the bottom line depends on how much methanol you need and where you are when you order it. So a typical example is a person in Midwest that order a truckload of methanol actually has to pay a premium of 34% on this spot price of 42 cents a kilogram. I will use this example to further illustrate the cost analysis we've done for the methanol. So basically what we've done here is reverse calculate the target cost of hydrogen to be able to be competitive in the methanol market. So today, the retail price of methanol is 67 cents a kilogram. By breaking down this cost, we have isolated the cost of transport and syngas, which we think would be replaced by our costs of producing hydrogen and capturing carbon to have the syngas actually. And this leads us to a target cost and a cost to beat actually to be competitive of $2 a kilogram. Then what would be the takeaways? What is important in this analysis actually? There is two main points. First, in our research, there is a quote that was striking, is that today the methanol market is in equilibrium, so the demand is happy with methanol supply, which is true. It's true to some extent, actually. So we believe there is a strong growth in the methanol market, mainly driven by the fuel market. And we believe that this technology has the potential to accelerate these trends, just as China's demand for methanol had increased since they discovered they have very cheap feedstock and they can produce cheap methanol with that. So the first point is the target cost we've come up with. Actually, $2 a kilogram is much lower than the first target price we've been talking to with the hydrogen the hydrogen premium markets around $6 and $7. So this is an interesting market. It's a big opportunity, but it's much further down the road after we've gone through this learning curve and the production process have been improved. So we're using this analysis, we've done some assumptions, and we think that this cost position could be improved if some of these variables change, if the bigger picture changed. For example, a carbon tax could change this overall analysis and give us more room, a decrease in the cost of carbon capture similarly. I will hand it to Luc for a final conclusion on our analysis.
Thank you, Ismail. So to wrap it up, our objective was to provide JCAP with a roadmap for the artificial photosynthesis technology, and especially to give a target of the price of hydrogen and what markets would be opened at these different price levels. So we think that based on our analysis, that the first target would be a distributed hydrogen, around $6 to $7 a kilogram of hydrogen. Then going down to $4 to $5 would enable to address gaseous hydrogen markets currently served by tube trailers and liquid bulk. And we also believe that methanol and potentially other liquid fuels would be further down the road with a price target of hydrogen around $2. So obviously longer term. We also looked at sensitivities of external factors that would impact one way or another these cost targets. Electricity obviously would make it easier to displace current generation by electrolysis. Natural gas would have a big sensitivity on all SMR processes. They could make it easier or make it harder if they continue to decrease to displace current SMR production. And last, concerning the liquid fuels, an easy source and less costly source of CO2 would make it easier to manufacture liquid fuels with this technology. So we hope that this analysis will help JCAP in the further developments of the technology, which we believe can be a real game changer for carbon emissions, and we want to open it to questions. Thank you.
I might have missed the core technology. Is it the solar cell that makes very high voltages, or can't you use electronics to get high voltages, or is it some kind of catalyst that makes this all happen?
There's a few parts to the technology innovation. So one of it is the PV panel device that can generate the high enough voltage to be integrated in with the electrolysis step. So it's also the biggest innovation is the integration of all the processes. So there is already technology with the PV and then using electricity from the PV panels to an electrolyzer, but we're just combining the process to make it more efficient and just more distributed and modular.
Yeah, just to build on that, we cannot really talk too much about it because it's currently patent pending, but we understand it's about the geometry of that the integration is made more efficient.
Since nobody's asking all these questions, but just curious, why do you call it artificial photosynthesis? I mean, where did you? Is that just an acronym you're using? There's a lot of differences between photosynthesis and this.
Right. So normal photosynthesis takes in water and sunlight and nutrients from the soil to grow, and then with that nutrients in the plant, we get fossil fuel after a few million years. But we just kind of skipped a few million years and get the liquid fuel in the end. So it's kind of, so just taking energy from the sun and then using water and carbon that we have to make that fuel for energy.
Right. I think you're stressing it's different from photosynthesis in many key ways. We're not producing glucose, which is what plants use. But in part, it's a name meant to just illustrate that the primary inputs are simply water, sunlight, CO2. So that's the source of the name.
And then one other question, just a curious thing. So you don't think we can, you can make hydrogen rich enough syngas that we can just go combust that right directly? You wouldn't want to go, instead of having to make the methanol as a subsequent step. So you could have, I know that, all the IGCC coal plants, for instance, they combust the syngas, and syngas, you can then, you're probably making that as one of your intermediates anyways here. So did you consider any market for just the syngas and combusting it and making power from that directly? I'm just curious. Well, you could just burn the hydrogen. You could just burn the hydrogen as well, like this gentleman suggested. But you could, reuse the carbon maybe a little bit. Anyways.
So just to make sure I understood the question, why we didn't stop at the hydrogen step, right?
Well, the syngas, they use that in power plants as an intermediate right now, anyways. So, right.
Yeah. The ultimate goal of the artificial photosynthesis is to come with a high-density fuel that would ultimately be used for transportation, transportation fuel. And methanol in this sense makes more sense than hydrogen. Just in the switching cost we've been talking about, if you want to retrofit the distribution infrastructure just to fuel cars with hydrogen, it is much more costly than methanol. So we thought that it would be a credible first step because of this first element, and the second element just being that it's from hydrogen, it's just the closest, the shortest path from hydrogen to methanol. For this mainly two reasons.
Or as this gentleman suggests, you have the hydrogen economy for hydrogen coffee. You make a point of use hydrogen with this technique, so you wouldn't want to, is there a market for that? Did you check that out?
Actually, we've addressed all the hydrogen market. So if we have a very competitive price for hydrogen, we will recommend to go after all hydrogen markets. But after that, if we are competitive in that, we are also competitive in the other fuels, which is methanol, for example. It's just an additional market. Why be restricted to this one if we can be also competitive in the other one?